Hello class, welcome to our lesson today dealing with section 4.4. We're going to be going through what's known as the multiplication rule. We're going to start with some basic terminology pieces and how to solve the multiplication rule. So let's go ahead and get started with the first piece of information, which is what is the multiplication rule. The multiplication rule is typically an AND event, but what's different here is there's two different trials. So it'll be the probability of one thing happening and then the probability of something else happening, and you kind of multiply those two things together to figure out the probability in total. So there's going to be more than one trial. Unlike when we did the addition rule before, it was always just one trial. It was like this, or these things happening at the same time. That was where the overlap happened. This is going to be find the probability of an event, and then find the probability of another event, and then find the probability together. There's two ways that you can look at different events when there's multiple trials. One is an independent event. So two events are independent if the first event does not affect the second one. So things like rolling a die would be independent. Tossing a coin are independent. But if the two events do correlate somehow to one another, or the second event depends on the first event, then we have what's known as a dependent event. An example of that would be drawing something but not replacing it. So you draw something, put it off to the side, and then draw something else. Those would be examples of dependent events. Along with dependent events also comes something that's called conditional probability. Conditional probability says find the probability that something happens based upon something you already know. So for example, I could say, well, what's the probability I draw a king if I know the card is already a face card? So I already know something, so I've whittled the entire pool down a little bit to a new version or a smaller amount, and then I find the probability based on that. It's always denoted with this notation. So probability of event B given. So this line up and down means given event A has already occurred. So when you're dealing with conditional probability, it's the probability of something given that the other thing has already occurred. So independent and dependent event probability is just multiplying the probability of the first event times the probability of the second event. The difference is for dependent events, it's not just by itself. So for independent, it's find the probability of A, find the probability of B, multiply them together. For dependent, you have to find the probability of A first, then, assuming that event A has happened, then find the probability of event B happening. That's why this is a conditional piece, because it's find the probability of event B given that event A has occurred and happened. So let's start with our standard 52 deck of cards. Find the probability of drawing 3 aces. So there's 4 aces in the deck. So the probability with replacement. So I draw a card, it's an ace. I put it back in and shuffle. So 4 out of 52 times 4 out of 52 times 4 out of 52, because each time I'm putting it back and reshuffling. I also wrote this in a different way. That's 1 over 13 to the third power. The only reason I said 1 out of 13 is I simplified 4 over 52, and then I raised it to the third because that's multiplying a number by itself 3 times. I get 0.000455. And so that's 3 significant digits there. So typically in these scenarios, when the decimals get really small, it's probably 3 numbers after the zero. So that's 3 significant digits, something to keep track of there. If I ask the same question but without replacement, I start with the same 4 out of 52. So I got 52 cards. One of them is an ace, so I'm looking at it. But then I put that card off to the side. Now you look at the deck, shuffle it, but there's only 51 cards left. Well, 1 ace is already out, so I have 3 aces left. That's why it's 3 out of 51, and then 2 out of 50 because I do the same thing again. Notice that the probability goes way down. And you say, well, they're still pretty unlikely. I say, yes, that's true, but without replacement, look, it's 0.001. This one's 0.004. This one's about 3 times less likely to occur. You may notice on some of these questions that they're decimals with significant digits or round to the nearest hundredth or thousandth. When the numbers get really small, it's probably the significant digits of 3 significant digits. You may also find that these questions have fraction answers. Now, some calculators can work up to denominators of 1,000 or so, but in general, you may have to multiply across and do some cross-simplifying. So you may have to simplify these things down yourself in order to figure out what the what the fraction would be as you're looking at some of these questions. So, things to think about as you're looking at that situation, but you want to make sure that you're able to set them up and be able to explain how to find those answers. You'll have to do that for your test. The next question has the table idea that we've done before. So it says Purdue and IU graduates and whether they like football or basketball more. So first thing is add up all the boxes. So this one adds up to a nice around 100. So that was designed by myself to make it a little bit easier for us, but it could be any number. Okay, now notice this is different than what we did before. This is find the probability of one thing, then another, then another. And this first one says with replacement. So it's the first one says find the probability of the first person you pick is a basketball fan. So I would go to the basketball row, add those up, and that's 59 out of 100. Then the second and third are IU graduates. So IU graduates would be this column, and I add those up and I get 46. So it's 59 out of 100 times 46 out of 100 times 46 out of 100 because it's with replacement. I could have that as a decimal answer. I could have that as a fraction answer, depending on the situation. I rounded to 3 significant digits to find the decimal. The second one says find the probability all 3 are Purdue graduates, but it's without replacement, which is probably more of the sense of the question. You're probably looking, pick a person, put them off to the side, pick another person, put them off to the side, pick another person, and see what you get. So first off, there's 54 Purdue graduates out of the 100, and then I'm dropping it by 1 every time because I'm picking from the same category. I don't want you to fall into the trap that, oh, every time it's without replacement, I'm just going to go down by 1 on the top and bottom in the numerator and denominator, and that'll get me my answer, because it depends on what you're picking in the next time. For example, what if the first graduate was supposed to be Purdue, and then the second graduate was supposed to be from IU? Okay, that would be the 54 out of 100, but then 46 out of 99, because the first person wasn't an IU graduate. Again, you want to be able to set these up, find the decimals, make sure you're working with your calculator as needed, and simplifying fractions and writing fractions answers as you see fit. Okay, in general, there's a lot of 5% questions going on right now in Chapter 4. There's been, if it's unusual, then it's more than 5% off, or of what it should be. If it's unusual, the probability is less than 5%. There's also this guideline of 5% saying if the sample size I'm taking is really small, so it's less than 5% of the whole population, even if it's without replacement, I can treat them as being independent and treat it as with replacement. So if you notice you have a really small sample size and a large pool to choose from, you can probably assume you can just treat it as a without replacement question in terms of a with replacement question. So to look at this example, let's look at potato chip bags from the Frito-Lay factory. There's 100,000 bags. Okay, they're producing a bunch of bags, and they know that 50 of them are defective, so the rest of them, 99,950, are good to go. So if 10 bags are sampled, find the probability they're all ready to go. So the probability of the first one would be the 99,000 number divided by 100,000. But since technically this is without replacement, I should take those down by 1 over and over again until I do that 10 times. So what I've written is the first 3, but I have to keep going until I get to 10 numbers that I would be multiplying together. Not that this is impossible, but even plug into a calculator, that would take a very long time to plug in. There's also a high probability that you would mess a number up as you're plugging that in. So rather than going that route, which would give you the exact answer, we can do this idea of, well, there's so many bags. Let's just go through and figure out what the first one is and just raise that to the 10th power or do that 10 times. And the logic behind that is the difference between these fractions, like this first one here and this second one, is so minuscule, it's not going to really affect your final answer. So rather than doing that, we just say, well, let's just make it easier on ourselves. Find the probability that one's defective and then just raise that to the 10th power, okay, and assuming that they're, not defective, and they're good for shipping. And then raise that to the 10th power to assume that they're all good for shipping. And the difference is negligible. It's going to go to the nearest 1,000th or 10,000th, and it's going to be fine. So in this case, 99.5% or 0.995 of the chip bags are ready to go. That's the probability that the 10 I pick are ready to go. So what does Frito-Lay do? Unless there's a big issue, they ship them all out. And if you get a defective bag, either the store is going to catch it and let them know, hey, we got some of the defective bags. Can you send us new ones? Or the customer gets it, and if you notice on the back of of bags of chips or any product like that, there's a customer number that you could call if you're not satisfied, and they'll figure something out with you, or even give you a free bag probably, and they let the customer figure out if it's defective or not, and then they kind of move on from there because it's not worth their time or money to figure out where the 50 defective ones are. Now, if that number were to grow a lot, then you would have a problem, okay, and they would probably have to deal with it on their end. But if it's a small amount of defects, that happens from time to time. That's why there's things like warranties on products and things of that nature. Next question says we look at birthdays that occur on the same day of the week. So the first one says find the probability both people that you pick are born on Tuesday. So the probability the first person was born on Tuesday is 1 out of 7. Probability the second person is born on Tuesday is also 1 out of 7. So that would be 1 out of 49. The probability you're both born on the same day of the week, the question on the right side, is actually a much easier question. Here's what it comes down to. Let's say it's you and me. Okay, we want to see if we're born on the same day of the week. Only one person affects that. So let's say I was born on a Thursday. All you care about then is if you were also born on Thursday. Well, the probability you were born on Thursday is 1 out of 7. So the first person just says, well, which day do we pick? Which doesn't really matter. And then the second person, it would affect the 1/7 then. So that's why it's 1/7. That's a higher probability than if it was just Tuesday, which makes sense as you're looking at that situation. The next question is tossing of a fair coin. You should assume all coins are fair, so you toss the coin. Find the probability of getting tails if I toss the coin 15 times and I want all tails. So first off, in your mind you should say, this is very unlikely. It's unlikely I'm going to get 15 tails in a row, which is true. The probability of the first one being tails is 1/2, and it's times a half, times a half, times a half, times a half, 15 times. So the easiest way to do that is 1/2 to the 15th power. This is a really small decimal. I will say this is one of the situations you want to know how to find the fraction. The easiest way to find this fraction would be to take 1 to the 15th, which is 1, and then take 2 to the 15th, which is this 32,000 number. But you'll probably have to do that individually. A lot of your calculators aren't sophisticated enough because they don't go to high enough fraction powers to be able to find that by just taking 1/2 to the 15th. So you want to make sure you're able to find the fraction for that situation. So check that out and make sure you're able to find that. Either way, if you said you tossed a coin 15 times and got all tails, I'm going to say, yeah, right, I don't believe you. Prove it or something, because the probability is so unlikely that I probably wouldn't believe you. Okay, the last thing that we're going to talk about is what's known as redundancy. This is something in mechanical systems, things like cars. So, for example, the electric wiring of my one of my vehicles went out, and so they would have had to rerun all the electric wiring. So what do? They just have a second set of wiring already there. Now, if they both go out, I've got a problem. Okay, but if one goes out, then I can just kind of switch it around and then use the other one. That's the same idea with aircraft. So let's say a plane's up in the air, okay, and your first system fails. Well, then you just unplug and plug into the second system, and hopefully that'll at least get you back on the ground. Okay, and so that's why there's so few issues about that, or when you see mechanical failure or something like that, they can still make it back to an airport of some type. Now, they may have to make an emergency landing or things like that, but a lot of those situations, the redundancy helps out a lot. So the probability one system fails is 0.001. That's 0.1%. That's pretty unlikely. To have both systems fail in the matter of you're on the plane or you're in the car or something like that mechanically, it's 0.001 to the second power times itself, which is 0.00001 or 0.001%. So the redundancy idea in electrical and mechanical system allows you to have a backup, so at least you can complete the task that you're working on, and then you can rewire or get a second set of wiring back up, and then you can keep moving from there. The idea of redundancy is helpful in those situations of mechanical and electrical systems. This was a base understanding of the multiplication properties. Remember, you want to know dependent versus independent. You also want to know the notation for conditional probability and be able to multiply those pieces together. Make sure you're able to show your work because you're going to have to do that on a test situation, and how to find the decimals and fractions as needed. Have a good day, everyone.